solar cells, a very experimental study. I will start with a short introduction to perovskite solar cells, but after a great introduction from Matthias, I don't think we need much. Then I will talk about the system I built at EPFL to measure stability. I will talk a little bit about the degradation of perovskite solar cells and our efforts to establish some kind of common ground for measuring those devices. And then I will talk about what I'm doing at Fluxim these days. So after a dramatic increase in efficiency of perovskite solar cells, the focus is now shifting to the next topic, next goal that we need to achieve to commercialize technology, which is the stability, which along then with a cheap method to process it on large scale are the three things that we have to achieve for the technology to be commercially viable. And when talking about the stability of perovskite solar cells, we have issues at different levels that we have to consider. We have the intrinsic factors related to the perovskite stability, such as illumination instability or sensitivity to high temperatures, which are very fundamental and cannot be really excluded without modifying the perovskite itself. Then we have, on a higher level, issues related to the device stack itself. So, for example, we know that some combinations of materials are not compatible with each other and may chemically react and degrade the device. And these, again, cannot be changed without modifying the device stack. And then finally, we have the extrinsic factors, which can be avoided with encapsulation, such as UV light, oxygen, humidity, and they can be avoided. It's usually those that will ultimately determine the device stability and also the cost of encapsulation. As Professor Tiwari said, this will ultimately lead to the most of the cost of the solar cell itself. On top of that, for a new technology which is not really well understood yet, we have a question on how to measure the stability in the first place. And this problem is aggravated by the fact that actually there are no good instruments available commercially to do those measurements. So I'm going to start by talking what I had to do all the experiments on the stability, which is by building a setup that can do all those sorts of measurements. And its basis is the environmental chamber, inside which we put a Peltier element. This is a heat pump that can cool or heat the device. On top of that, we have a copper plate with a thermometer, and we press the device against that heating or cooling stage. And we close the chamber with a piece of glass. And then we have different subsystems to control different environmental conditions inside the chamber, and they are controlled from one PC. So for example, for temperature, we have a PID controller that takes the readout of the temperature of the sample, takes the set point of from the user, and biases the device in such a way to reach the desired temperature by either heating up or cooling the device. So you can control temperature very precisely and locally in this manner. Then each channel or each pixel, each device on our substrate is connected to a separate channel of the potentiostat. And like that, we can keep the device at the desired conditions, be it maximum power point or constant voltage, constant current, GSC, VOC. We're pretty flexible here. Then the next subsystem is control of the illumination. And here we have control. We have choice of two different illumination sources, either a solar simulator with UV light or a white LED lamp, which is much easier to control, but doesn't have any UV component. And we have a photodiode to create a feedback system with a LED driver to control very precisely the level of illumination. And then finally, we have different gases that we can feed into the chamber. And we use mass flow controllers to feed those gases into the chamber. And these are kind of electromechanical valves with a feedback loop already inside. So you can control precisely how much gas you want to let in. And like that, you can engineer the atmosphere. For example, you can have 1% oxygen in, otherwise nitrogen, and 10% humidity, which we can then read with this sensor at the outlet. So this is the system as a whole, and we then soon realized that the power cuts at EPFL, which happen around once every 6 months, are frequent enough to ruin a lot of experiments. So we put a backup power supply with a big battery, and also backed up the whole room with a diesel generator line. So this way, experiments could run for long enough, and that's what required. So we had 4 holders, which could hold 32 devices, and the system was bench size, like 1 by 6 meters, more or less. And then we could do all the science, finally. So, as I mentioned, now the stability became a key topic in perovskite research. And unfortunately, we have no consensus on how to measure stability. So it's a little bit annoying problem because people measure stability in different ways, which are not comparable with each other. So for example, we have here what they call a dark drawer test, where people keep the devices in the dark, in a drawer, and measure them periodically. Then on the other hand, we have studies which do maximal power point tracking under illumination, encapsulated devices, well-controlled conditions, and it shouldn't be surprising to you that this device, although it looks similarly stable to this one, cannot be compared one-to-one like that. So what we need is some kind of consensus on how to measure stability, some kind of metrics which would be akin to what we have for efficiency of measurement of perovskite solar cells. Those were also modified a little bit to account for the hysteresis, for example, and now doing maximal power point tracking for a few minutes is standard for measurement of efficiency of perovskite solar cells. So what we did is we took our standard devices, our workhorse architecture, with FTO, titanium dioxide compact layer, then a mesoporous layer, and then infiltrated with a perovskite with a big overlayer, and completed the device with spiro omitat, that's a whole transport layer, and a gold electrode. And the perovskite that we used is what we call a triple cation. It's a mixture of cesium, methylammonium, and foramidimium on the cation side, and iodine and bromine on the anion side. And we fabricated around, I think, 250 devices for the study. And the reason why we chose this architecture is that we can get consistently very good efficiency, over 20%. And we also get a relatively good room temperature stability, relatively to what the field is accustomed to. And I'll talk about this kink here a little bit later. So we systematically tried changing one parameter by another parameter and measure bunches of devices between 8 and 16 for each condition, and then compare what really degrades those devices. So here, as the first thing, we compared the spectrum of light. So we have the UV light and the white light, or like white plus UV and white light. And we see that although the devices degrade a little bit more at under UV light, this is by no means a catastrophic change. So it has an effect, but this is not the main factor that degrades perovskite solar cells. Even though we're using here a titanium dioxide layer, which is known to be a UV catalyst, so in a way we check the worst case scenario, and it's still not catastrophic. Then the next thing what we did is to cycle the light. I mean, any solar cell endures daylight cycles over the 24 hours every day. So what we did, we compared we took the curve device age continuously, and then we left it in the dark for a few hours, and we remeasured the efficiency. And what you see here is that a lot of efficiency is actually recovered when the device is left in the dark. And this roughly corresponds to this initial efficiency loss. A little bit, it looks a little bit like burn-in in OPV, but it's actually not. It's a reversible process. And I'm going to talk in a minute why. And then what we did as a next step, we cycled the device every 12 hours. And you see that the degradation is actually less than when the device is exposed to light continuously, and it nicely recovers every day. So what we were trying to see is if there would be any light fatigue from the cycling, but what we found is actually it's the opposite. When the device is in the dark, it just doesn't degrade, so there is no light fatigue. We call this phenomenon good night sleep, and we explained it by investigating how ions move inside the device. And as it turns out, the cations that are mobile in this material can move on a long time scale of hours and accumulate the interfaces and modify the efficiency. But then when you leave them in the dark, the device can fully recover. Then the next thing we checked was the effect of atmosphere. And we fed the chamber with different gases. So here you see the curve under nitrogen, what I already showed before. Again, maximum power point tracking, 20 degrees, one sun. All the measurements are now with white LED illumination. And when we added oxygen to the chamber, you see that the device degraded catastrophically faster. And then we see that addition of further 5% of water doesn't really change things so much. But when we added 100% relative humidity, the device dies immediately within several hours. But it's not fair to talk about about atmosphere without mentioning illumination, because the two are strongly connected. And actually, a lot of mechanisms for degradation that were proposed for perovskite solar cells require photooxidation step. So what we did is we did all those measurements as well in the dark. So as you see, when we keep the devices in nitrogen in the dark, unsurprisingly, they don't degrade. The same in the dry air. With 5% of humidity, they degrade a little bit. Looks like they hydrate a little bit at the beginning and then stay stable. But then with a lot of water, they degrade regardless of illumination. So it looks like oxygen plus light is bad, but water doesn't require light to destroy the perovskite. It can do it on its own. Then the next thing we tried was to control the temperature. And again, this is the curve at 20 degrees. This is the same reference curve you already seen. When we cool the device to minus 10 degrees, we lose a lot of efficiency because pyro, the organic layer, doesn't conduct so well anymore, but the device is stable. When we heat up the device to 65 degrees, again, we lose a lot of efficiency. We lose a lot of open circuit voltage, like in any solar cell. But then the device degrades pretty catastrophically over a short period of time. And then the next thing we asked ourselves is that what if we cycle the device between minus 10 and 65? Is there some temperature fatigue? But in fact, the device that was cycled degraded less than the device that was kept at 65 degrees. And when we zoomed into the curve, it turns out that the sustained degradation is only experienced when the device is 65 degrees, and at minus 10 we have those long transients because the maximum power point changes and the ions have to rearrange a little bit. And then finally, of course, we checked also for the effect of light at high temperature, but we see that the device degrades regardless of illumination. So temperature is really a critical factor that can destroy perovskite solar cells with certain architectures, and by itself it can be pretty harmful. So why it degrades so much at 65 degrees? We did secondary ion mass spectrometry on our device, a cross-section, when we drill into the device and we see what ions are there and where. And I'll just go through it very quickly. But here we have a gold electrode. And what we found in a sample which was aged at 70 degrees in the dark is that a lot of gold can accumulate deep inside the perovskite. So it looks like it goes straight through spiral and then it can accumulate deep inside the device, and we did some other experiments to confirm that this is indeed the cause of degradation and should be avoided by changing the device stack. So you can see also here this layer of gold deep inside the device, but I'll not go into much detail about it. I will move on to the next parameter that we varied in our study, which was the load on a device. Of course, when you age a device, you have to choose what electrical loading you want, either VOC, other point along the JV curve. Here we check the first three, and what we would do, we would measure a JV curve and then keep the device at one of those conditions and loop this procedure for 250 hours, then let the device rest in the dark and remeasure it. And what we found out is that at MPP, the devices actually degrade the least, and they also recover the most. At short circuit, they degraded a bit more, but they also recovered almost as much performance. But when we kept the device at open circuit, surprisingly, it degraded the most and recovered the least. So this is a little bit contrary to what one would think, because there is no current flowing inside the device. But then we compared also the other JV parameters to understand a little bit better. We see that the degradation is a combined effect of loss of VOC and a fill factor. And also the hysteresis evolution looks a little bit different for those devices. So while we didn't really explain why it's so, at VOC, all the charges have to recombine, so you have a high charge density, and with all those proposed photooxidation mechanism, perhaps the trace oxygen in the chamber can react with the high number of charges and photochemically degrade the device like that. But that's just a hypothesis that we didn't really verify. So then from experience and looking at many GV curves, stability curves, you start to develop a little bit of sense how they look like and what the components are. And when we use what I would call non-aggressive conditions of illumination, MPP, and room temperature, this is usually what we would see. We would see this exponential regime, which I already said it's a reversible degradation, and then a linear decay, and followed by a recovery of more or less this regime if we keep the device in the dark. And now, I already mentioned we don't really have any metrics to compare stability of perovskite devices, and I think a good starting point would be to start reporting the T80 from measuring this linear decay and fitting the curve. T80 is a parameter which describes how much time it takes the device to lose 20% of its efficiency. In our case, it would have to be discounted for this exponential decay. And there is now a big discussion on this and how to measure those devices and how to report some parameters. And so I'm looking forward to the conference in China on that topic specifically, ISOs 11. I'm sure I hope we will make some conclusions on what the best things are, what the best ways are to measure the stability. So this is what we think based on those measurements, how it's most reliable, remembering that the technology is still at early stages and it's not very well understood how those devices degrade. So it's a little bit of a conservative estimate. We think that one sun solar simulator is the best. Of course, this is the real illumination the solar cell has to withstand. But I think it should be possible to relax it to white LEDs, given that using a solar simulator is very tedious, and the solar simulators, the light bulbs degrade on a similar timescale as your device, so it's really hard to measure like that. For the load, MPP is of course the real load on a device. That's what solar cell has to take in the field. But from our study, it looks like measuring at VOC or JST gives you a conservative estimate, so should be also probably should also be acceptable. For the temperature, I already said that high temperature is the key stress factor. So I think everyone that measures the devices and wants to put a stable label should. Although measuring at the low temperature, the room temperature, has an advantage that you can disentangle different factors that degrade the device and help you understand a little bit. And then for the atmosphere, we used only unencapsulated devices in this study and flashed the chambers with different gases. And the reason why we didn't encapsulate is that the quality of encapsulation into our study. So bad encapsulation could give us a bad stability, which would not necessarily be related to other factors. But perhaps the best way to do these things is to encapsulate and then still use blanket atmosphere to protect the devices, because what we did only protects the ingress of oxygen and water, but doesn't really protect against the decomposition of perovskite and stuff evaporating. And I hope there will be more studies like that in the future on different architectures as well, and I hope we can converge on some way, some standards to measure the stability of those devices. So this is a little bit of an off-topic but interesting story that happened related to this work. And how do you know your work is good? You know it's good when someone copies it and pastes it one-to-one, and it gets accepted without a single revision in an Elsevier journal. So this is what happened to us a few months ago. This is really, I don't know how it can happen, but the group from Pakistan, from Lahore University of Technology, managed to submit our paper and copy it one-to-one in this journal. And when we, I know, the only thing they changed was title, author list, and the figure captions. Otherwise, there was no revision at all. We contacted the editor to take it down, of course, and they told us that these cases usually take 1 year to resolve. And we published it everywhere on social media we could. And then the editor decided that in the end, things could be sped up a little bit, and they retracted the paper in a week. But they mixed up the retraction notice. They said that the authors self-plagiarized the other paper they published. There is a story that is being updated with the newest developments on this website that tracks retractions if you want to know more. Then finally, the very last part of my talk is what I'm doing at Fluxim right now, which is to take this, what we build at EPFL, improve it, and put it into a product that can be used to measure stability reliably and with high degree of control of the environment. So this will be a compact tool that can measure the degradation of OLEDs and also LEDs, OLEDs. It will have a wide range of stretching techniques such as MPP, VOC, JSC, or any point along the JV curve. We can control temperature, we can control atmosphere, we can control illumination. We can fit up to 32 devices in this instrument. It's fully automated. The sample design also can take any sample which is up to 2 inch by 2 inch. And we have this instrument in PV, OLED, also in a hybrid version. So for solar cells, we can stress at any of those conditions. By default option, we have LED illumination with a white and UV component, which are separately controlled, so you can change the ratio as well. For accelerated aging, we can do up to more than 10 suns illumination equivalent, and I think that's the step where this technology is going. We already can have devices that last for thousands of hours, so we have to accelerate soon. We can control temperature up to 150 degrees, also for accelerated aging. We can do in situ UV absorption to detect bleaching of the film, also PL and EL. For the OLEDs, we can age by constant current, light, or voltage. We are compatible with both bottom and top emitting devices. We can have a spectrometer in situ to measure the spectrum, so you can get luminance as well like that. And we have a patented OLED acceleration testing procedure where you do a matrix of different temperatures and different currents, and from there you can get an acceleration factor and deduce the lifetime of your OLED, reducing the measurement time more or less by a factor of 10. So we can also combine this instrument with our workhorse characterization platform. And you will hear the workshop on Paios today. But what it can do all of different sorts of electrical measurements, like very precise GV characteristics, many different transient techniques, impedance spectroscopy, and we can also do all those measurements as a function of temperature if we use those two instruments combined. And then finally, we can combine several of those instruments and daisy chain Paios through all of them, so that Paios does sequentially measurements of each single device that we put in there. And for example, we can measure an impedance spectrum of each device every 20 minutes, or do a transient measurement every half hour, or whatever you want. And this way we can understand really the degradation in much more detail than we would just by having a curve of efficiency versus time. So this instrument will be available in spring next year, and I'm very excited that it's coming soon. So with that, let me quickly conclude. I talked about the infrastructure built at EPFL to measure stability of solar cells. I talked about the new challenges that the technology, which is not well understood yet, poses for measurement of stability. I said that aging under light, maximal power point, and both room and high temperature is now the most reliable way, the safest way to deduce the stability of perovskite cells. I talked about the dedicated aging protocols are urgently needed to be developed by our community. And finally, I told you about doing at Fluxim right now with relation to the next generation stability measurement instrumentations. And with that, I would like to thank the team at Fluxim as well as my collaborators at EPFL and you for your attention, and I'm happy to answer any questions. So a lot of this effort is happening at the ISO's meetings, International of Organic and Perovskite Solar Cells. These are annual meetings when there are discussions and some draft protocols drafted. The big success of ISOs in the past was to come up with protocols for OPV. And now the work is going into the direction of creating a protocol or modifying the existing protocols for perovskite solar cells as well. So this meeting happens annually in fall, if you're interested.
I have one question regarding stability problem. So I'm not in this perovskite community, but so far I understood there was always this problem with degradation. Now you show it recovers overnight. So is there no problem anymore? Or because in real world you have always a night to recover, everything is perfect. Can we now use it? Is everything fine if you encapsulate them and you do not have oxygen or water? Or how do you see the situation?
I mean, you still have the linear component degradation, which is much slower, but nevertheless, still pretty bad. So if you see look at this curve, yes, there is this. Most of the degradation is reversible on this timescale, but there is also this component. And I think if you translated this linear degradation to assuming that it's fully linear with illumination time and intensity, and assuming 4 hours of daylight a day, you would arrive at somewhere between 2 and 3 years. But of course, the things are improving, and I'm convinced that eventually we'll crack it. But there is still a way to go before.
Because if you go to the plot where you show the daily measurement, you see the degradation was not so strong.
Yeah, and that's true. In that particular case. Yeah. But yeah, that was this particular device. Maybe it didn't degrade as much. But I mean, here we have, I showed data with much more statistics where it's clear that it degrades. I don't think these two regions are sequential, if that's what you mean. I think this linear component is always there. You just don't see it so much at the beginning.
Okay, there are no more questions, so let's thank Konrad again.